Welcome to the e-Pathshala lecture series on computer science for postgraduate students. We are in the 19th module of the lecture series for the subject computer graphics and visualization. We had 18 modules earlier, and the previous module, the 18th module, we discussed about color models, where we talked about the most popularly used color models like RGB, CMY, the HSV, HLS color models, and so on. In this session today, in this module, we will be talking about rendering, an important concept, an important topic as far as computer graphics is concerned. The subject of rendering is too vast, and since we have a shortage of time, we will be talking about the fundamentals of the concept of rendering. Okay. So, rendering involves, or rendering in 3D is all about imitating the real world as closely as possible. As we discussed earlier in the previous modules, our aim in 3D is to imitate the real world as closely as possible and give it a real life like object, feeling of a real life object. So, what shall we do, or what do we do to achieve this, what is called visual realism? So, let us learn more about it. The learning objectives are to understand how to apply shading models, textures and shadows for visual realism. So, this is our objective. To also understand the techniques of ray tracing, an important technique used for rendering. These are the keywords. Let us understand what is actually visual realism. In the case of 3D graphics, as we know, so we can create a lot of objects, but how do we give them the real life like objects, a real object like feeling? So, for this we have various stages through which we should go so that we achieve the objective of visual realism. So, the stages of visual realism, as you can see, are wireframe model. First we will be forming a wireframe model of an object, which is the skeletal version of the object, you can call it as, the flat shaded version, the smooth shaded version. Then we will proceed to the lighting. So, we can add lighting to the 3D scene that we have created. We can add textures, and we will be adding shadows and some materials, or we will be giving some material properties, and finally some kind of environmental maps or bump maps or MIP maps, so that for some objects they are so highly reflective that the surrounding environment is seen on the surface of the objects. So, because of the material properties with which the surface is made up of. This is where giving visual realism involves a sequence of steps which are to be followed. So, what is actually rendering? So, we will be computing the color of a pixel given a chosen viewing position. So, what should be the final color of a pixel? So, for example, imagine a 3D world, a collection of objects are there, and now we are choosing a position in the 3D world, and now we are taking a view of the 3D world. So, from the chosen position and the orientation, so how the world appears, because as we know in the real world, depending on where we stand and depending on how we orient ourselves, we will have a different view of the world. So, the same thing we are going to imitate here in the 3D simulated world. So, visual realism is how to model 3D objects that look exactly similar to real world objects. So, in essence, it is simulation of the real world. So, let us see how the objects are rendered. So, you can see here on the screen you have a wireframe model. So, this is the wireframe model. Then we are applying some shading. So, we call it flat shading. Then we further tweak it, and so we give it a more what is called, we add more lighting conditions, we add more lights, we compute the reflection properties, we assume some material properties for the various objects, and so on and so forth, so that we compute the final light that gets reflected from the surface of the objects, and so that they appear as realistic as possible. So, then we further add textures, and as you can see in the last picture here, some textures are added, so that depending on what texture we add, it appears to be made up of that object. So, that is where this texture here looks like made up of wooden. It is a wood texture that we have applied on the object. So, that is how we achieve visual realism. So what is a shading model? So we are going to start looking at the first, so in the sequence of visual realism, or for achieving visual realism we follow a sequence of steps, as I said. So the first thing is the wireframe model. The wireframe model is a skeletal version of the 3D world, or the objects in the 3D world. So we are applying shading. Once the wireframe model is there, the next step is to apply shading. So shading is the essence of shading, or the idea of shading is to compute the interactions of light with the surfaces of the object. So how do we compute the light interactions? Or say there is a light and the light is incident upon an object, and how the object reflects light, or how the object absorbs light, or with what materials the objects are made up of, so that their surface properties are evident, and when we observe the objects from a distance, how do they appear. So all this computation of light, or interactions of light with various surfaces of objects, is all done in the shading model. So as you can see here, a shading model dictates how light is scattered or reflected from a surface. Assume that there are two types of lights that illuminate objects in a scene. So for simplicity we can assume that the world is illuminated. The world here means the 3D world, that is the imaginary 3D world, is illuminated by lights from external sources, which can be point lights or ambient light it can be. So the daylight, so that we can assume. So a shading model, the job of a shading model is to compute the amount of colored light that gets reflected from a surface given a viewing position. So finally what we observe is the reflected light, and given a viewing position, given a set of lights, and assuming the light properties, assuming the material properties, so how much light gets reflected, or and what we see actually in our eye is what is to be computed. So the shading model does a big job of computing light interactions with surfaces of objects. So how does the light interact with objects in a 3D world? So we can take the real world analogy again. An object can be a black body, an object can be highly reflective, an object can be made up of, say, a combination of reflective and absorptive properties. It is something like whatever light that is incident on an object, if it gets completely absorbed, we call it a black body. As you can see here in the picture, when the light is incident upon a black body, the whole of the light gets absorbed and nothing gets reflected. So but what we observe is a reflected light. Okay, what we observe is only the reflected light. So a black body is something like whatever light that is incident absorbs the whole light, so it appears black or dark. So unlike that, we have another kind of object where, say, if the surface of the object is imagined to be like this, very much ruggy, rough, and it is made up of what is called very rough texturey kind of surface. So when light is incident, some light is absorbed, some light is reflected in multiple directions. So that is called diffuse reflection. So a part of the light is absorbed and some part of the light gets reflected in all directions equally. The other kind of reflection is specular reflection. So in the kind of surfaces that exhibit this property are like, say, where when the light is incident, the whole of the light gets reflected in only one particular direction. So that means you will see what is called a bright spot on the surface, or that is called specular highlight. So as we can observe that most of the surfaces exhibit both specular and diffuse properties for their surfaces. So let us see how light computation is done, how the interaction of light with objects is done. So what are the factors that are involved, or what are the computational parameters that are taken into account? Here the amount of light incident, so how much light is falling on the object, the color of the incident light, so color also matters, the relation between viewing direction and the incident direction, it is also important because we are viewing from somewhere, the light is incident, and if it does not get reflected in the direction of viewing, we do not have to bother about computing the light in the direction of viewing. And the surface properties of objects, because they are going to define whether the light, how much of light should get reflected from the surfaces. The type of the light sources in the scene the reflective properties of neighboring objects. So sometimes the neighboring objects also play a major role, and ambient light and its color as well. So colored light also influences the way that we observe a light or the reflected light. So interaction of light with objects can be categorized into two, which is diffuse scattering and specular reflections. As we discussed earlier, a diffuse scattering is where the amount of light incident on the object, a part of it is reflected in all possible directions, a part of the light is absorbed. So as you can see, a ball like object is shown here. When it is made up of material with diffuse properties, it will appear like this. But when an object is made up of metals, or maybe like plastic like objects, or like say shiny surfaces, whatever light that falls on the object, most of the light gets reflected in a specific direction. So that is why you would see what is called a specular highlight. This is called, this bright spot on the surface is called a specular highlight. So as I said earlier, most of the objects are made up of surfaces or materials which exhibit a combination of both diffuse and specular properties. So flat shading is a basic version of shading where we tend not to bother much about the various undulations or the kinds of surface properties. What we do is we imagine the surfaces are made up of polygonal flat faces, and also that we consider one polygonal face on the object, and we compute the normal vector for that, compute the amount of reflected light assuming a given light source and a viewing direction, and then for the whole of the polygonal face we will be applying the same color or the same intensity. So that is where because we apply the same color throughout the polygonal face, as you can see here, the donut like object here appears jagged and roughed up, as all the individual polygonal faces are very much clear. With shading techniques, better shading techniques like smooth shading techniques, which we will be seeing later, we will be able to give the object a very smooth like appearance. So as you can see in the smooth shading, there are two standard shading techniques used. One is Gouraud shading, the other one is Phong shading. In the case of Gouraud shading, we interpolate the colors assuming the vertices of a polygonal face are given various colors, and we try to interpolate the in between colors between two vertices. So we interpolate the colors between two known vertex colors. While in the case of Phong shading, the normal vectors are interpolated. So unlike Gouraud shading, here the normal vectors are interpolated. As we know from earlier discussions, normal vectors is an important component of 3D world, because normal vectors identify the orientation of an object in the 3D world. So what we will do is we will be computing the normal vectors of various vertices, and then we will be interpolating the normal vector directions. So that is more accurate and it gives a better surface than the Gouraud shading. So as you can see, the flat shaded one, a ball flat shaded appears like so what is called tessellated. A Gouraud shading one appears like this, and a Phong shading one is so perfect and smooth. So the light sources, so once the shading is done, shading models are done, so we can also imagine the light sources in the 3D world. So we can imagine four types of lights. One is the point light, the other one is the direction light, the spotlight, and the area light. So light also has got properties. So as you can imagine, light can be directional, so we have a direction for it. You can attenuate, that is you can fix up a distance after which the light intensity dies, or it's the attenuation. You can imagine the light properties like diffuse, ambient, specular. The color of the light is also an important factor which we can consider. So here let us go further into the next level of visual realism, which is applying textures. So we have added lights, we have computed the shading model, or we have used the shading model, and the next step is to add textures. So by adding proper textures, we would get a feel for the kind of material with which the object is made. So in 3D graphics, we can make surfaces look more realistic by trying various textures like which are made up of either bitmap or procedural. What is a texture? Texture is fundamentally an image. Okay, what we will do is, it is something like say imagine you wanted a globe like object. You can imagine a sphere like thing. First what you would do is, you would take a sphere and then you would wrap around a sheet of a printed flat globe. You would wrap around that sheet around the spherical surface. So that is what we are going to do here. We are going to imagine a 2D map, and then we wrap around the 2D map object of choice. So this is there are two ways in which you can imagine a texture. One is either you can imagine a bitmap, or you can use a mathematical equation to create a bitmap. Okay. So to create a map or to create a procedure that creates an image or an intensity value. So how do we apply textures given a 3D object in the 3D world, and we have now a texture which is a 2D image. Okay. Now as you can see here, this is the 3D object which is a cylindrical surface, and this is the bitmap image which we would like to use it as texture. So we are trying to take this texture and wrap it around the cylindrical surface. So how do we do is, our aim is to find for every position on the cylinder or the cylindrical surface, we try to compute or we try to find an equivalent pixel from the bitmap texture image. So once this image is now being used as texture, for texture image, it is called it is a texture, and it is in 2D world. So for every pixel on the cylinder, or for every position on the cylinder, we will be using we will be computing or we will be selecting a position on the 2D world. So this in between 0, 0 and 1, 1 space is called the texture space. So we are in the pixel world, or once we collect a pixel and then use it as a texture, we call it a texel. Pixel and texel. So okay. Once the texel is used to map or to attach to a 3D position, now the texture we say is applied to the 3D object. So that is how we do it in the reverse order. So this is the texture space. For every position here, we normalize the bitmap 2D space into texture space, which is between 0, 0 and 1, 1. So we take each and every point and we convert that into an equivalent value, and we find a suitable pixel here, a suitable position here. Okay, now you can see this order: the image space, okay, a texture space, the object space, the viewing space, and the screen space. So the arrow marks are in the reverse direction. Okay, you should observe that. So we will be going it in the reverse direction. Okay, screen space, viewing space, object space, texture space, and in the image space. Okay, the texture space is the normalized version of the image space. Okay, this is what is the texture space. And textures also can be used, or like say the bitmaps also can be used to create roughness on surfaces. For example, you can imagine orange. The orange surface is such that there are a lot of dimples on the surface. So the surface is not smooth like your ball or spherical surfaces, perfectly spherical. Orange is spherical, but its surface is it has got a lot of dimples. Dimples are lows on the surface. Or the low means it's a valley like, or it's a low. As you can see here on the teapot, there are a lot of dimples. So how do we create such a surface? Is we can use the bitmap or the texture space, and we can try to perturb the normal vectors of the surface of the object by perturbing the normal vectors according to the texture values or according to the intensity values in the texture space. So that is where we can modulate. This modulation gives us a feeling that, so what we can do is, on the low you can redirect the normal vector so that it sees in a different direction, so that the reflection at that point is almost minimal. Okay, when no light is reflected from a point, it appears as if it is a dimple. Okay, otherwise it is a high. So it is a low and it is high. So we can recreate such surfaces which have dimples like orange, the surface of an orange with by modulating the normal vector using the texture values. And reflection mapping is one another technique where you can reflect the surrounding environment on the surfaces of objects. Often you can see when somebody wears a spectacle, you can see the surrounding environment seen on the spectacle. So that is the nearby objects or the objects in the outer world are seen on the surfaces of the highly reflective metallic objects. Like as you can see here, the metal teapot, the surrounding environment is seen on the surface. So this can be done by techniques like ray tracing. We will see further. The shadows is the next step of visual realism. So once we add lights, it is obvious that there are shadows. So if the light is unlike an ambient light, there will be a shadow. Okay. So how do we compute shadow, or how do we create a feeling that the object is casting a shadow? So for that, what we can do is we can imagine a light source, and we can compute, we can take projections of all the faces of the object. Imagine a cube. There are 6 faces for the cube. Now you can imagine a light source. You can compute the projected version of the of each of the faces on a flat plane, which is basically the ground. Okay. So once we add up all the projected versions of all the 6 faces on a planar surface like ground, we will, once the projected versions are summed up, we will get the shadow shape. So the shape of the shadow is computed by summing up all the projected versions of all the possible faces of an object. Here the example given is for a cube. You can read here further, which you would understand better. So the last step in the towards visual realism is ray tracing. Ray tracing is such a fantastic technique where it's so complex. It takes quite a lot of time. The algorithms are so complex that to give us a real lifelike object a feeling, it's very difficult because of lot of interactions of light, because of the colored conditions of the light, because of the viewing positions chosen, because of interactions of light with various objects, and because of the surface properties of the objects, we get to see various kinds of surfaces and objects. Ray tracing is a global illumination based rendering method for generating realistic images on the computer. So adding realism is so fundamental, and it is the ultimate objective. The advantages of ray tracing are to enhance visual realism, lighting simulation, hidden surface removal, shadow calculation, texturing, reflections and transparency. As you can see here, a principle of ray tracing is to calculate what is called, that is the amount of light that reaches a given pixel position. So imagine we are standing here and we are seeing the world, and before your eyes you can imagine a rectangular grid. The grid is our viewing area. Okay. In the grid, for each pixel position, you can start with the first pixel position on top, and you can fire a ray into the 3D world, and the light or the ray hits various objects while it moves. Imagine the the ray hits the objects in the 3D world. When it hits, depending on the surface properties of the object, the ray will take multiple directions. Some of the light rays get absorbed, and some of the light rays you can divide the light rays or the intensities further, and you should track the ray till it reaches the light source, because say we have to track a ray from the grid position or from every pixel position on the grid towards the light source. Why? It is, in fact, you can imagine, okay, why it should be done like that. In fact, every light originates from a light source, and then it reflects and refracts, and then it gets absorbed, and finally lot of light rays go in multiple directions. And in fact, we should track the light ray like that? No. Why? Because we are not interested in all those light rays that emanate from the light source and then go in all possible directions, and which finally do not reach this grid, okay, which finally do not reach this grid. If we do that, that is, if we track the light from the source towards into various positions, we will be wasting a lot of time and resources, and thereby we lose a lot of processing power as well, wasting a lot of processing power as well. So instead, we will be selecting a pixel position on the grid, and we will be firing a ray into the 3D world, and it takes multiple directions, and we can calculate reflections and refractions, and the finally these should reach the light source. So, we will be calculating how much light intensity finally reaches the pixel position here. So, for every pixel position we should calculate this. So, for the entire grid, once we do this, we will get to see such fantastic images. As you can see here, these are the ray traced images. As you can notice, simple and ordinary images look like this, ordinary visuals look like this, but ray traced images look like this. As you can see how fantastically the reflections and refractions and the transparencies, there can be transparent objects, partly opaque and partly transparent objects. And imagine such complex objects in the 3D world, but we can still fantastically do this rendering of various objects so that they appear like real life, like by a ray tracing technique. With this we come to the end of the 19th module of the computer graphics and visualization subject. We will be continuing in the next module with the topic with the animation, which will be the next topic in the 20th module. Thank you.